We're going to start our unit on acids and bases, talking about properties of acids and bases, because for years that was the only way you could identify acids and bases, or really how they were the only way they were understood. Up until about 180, 200 years ago, there was no chemical definition for what an acid was and how it behaved. It was just basically defined by its properties. Okay, so we didn't know what types of molecules acids were back then. And the first way that a chemist would determine if something was acidic is literally to taste a small amount of it. And if it tasted sour, it was an acid. If it tasted really, really sour and even burned your tongue, it might be a strong acid. We don't do that anymore, of course. There's other ways of figuring out if something is acidic. So conducting electricity. Not all things that conduct electricity, of course, are acids, but acids do conduct electricity. We need to dissolve them. They neutralize bases and are neutralized by bases. Essentially, they just react, and we'll talk about those reactions a little bit later on, but they react to give you a salt, and they give you water and a neutral pH. They turn litmus paper red. There's all kinds of different indicators that we could have talked about there instead of litmus paper, but litmus is such a common one, commonly known one for testing, like the pH of pool water or aquarium water or basically any other solution. And then pH, we'll get back to the sort of mathematical definition later on, but I thought we'd hit on it here because everybody's heard of pH. If it's less than 7, solution's pH, that means it's acidic. And we'll talk more specifically about what that means on the molecular level later on. And then acids tend to corrode metals. Not all metals. If you remember back to talking about activity series, hydrogen, and you can look on the back of your periodic table and see the activity series, you'll see that hydrogen is about 2/3, 3/4 of the way down. And acids all contain hydrogen. So for example, hydrochloric acid is an acid, has hydrogen in it. And if you react it with zinc, you should get a reaction because zinc is above hydrogen on the activity series. And so when we say that hydrochloric acid corrodes zinc, what we really mean is that the zinc replaces the hydrogen and gives you aqueous zinc chloride and leaves you with hydrogen gas as well. And then of course we'd have to balance, which I think is just a 2 in front of HCl. But since the only solid in this whole equation is the zinc, it's really the zinc replacing the hydrogen in the aqueous solution, but it's described as the metal is being corroded because we don't have that solid anymore. We have aqueous zinc chloride and hydrogen gas given off. So it's just a single replacement reaction when that happens. It doesn't work for all metals. Like gold is resistant to things like acid rain because gold is below hydrogen on the activity series. So it would be a no reaction if you got some acid rain on a gold plated statue or something like that. It's not going to affect the gold. Bases. Bases are bitter. They don't taste sour, they taste bitter. And that's an important evolutionary adaptation for animals to taste bases as bitter because bases are often associated with poisons found in nature. So if you think about a lot of the chemicals that plants have to ward off insects and other animals, things like caffeine, the THC that's found in marijuana, nicotine that's found in tobacco plants, all of those are actually just plant pesticides. They don't kill humans usually unless taken in too large of an amount, but they have like a narcotic effect. They have either a stimulant or depressant effect, but they're basically just plant pesticides that are naturally evolved. But if you imagine going back in time to hunter-gatherer days, if you were in charge of picking plants for the rest of your family to eat, you're going to taste them. If it tastes bitter, you're probably gonna throw it out, not take it back to your family. That's going to be a survival advantage because it might be poisonous. That bitter taste is just, at some point in time, animals develop that to tell them that something was perhaps not good for them, and then stop eating it. And so, those plants would be avoided. Bitter taste, though, still is appealing to some people in some ways. I mean, as you get older, you become more tolerant of the bitter taste in like broccoli and Brussels sprouts and things like that. It's also found in, coffee and things. There's all kinds of places where it is still present in small amounts. Bases, just like acids, when you dissolve them, conduct electricity. They neutralize acids. Like when you take an antacid tablet, you're basically neutralizing the excess acid that's found in your stomach, if your stomach hurts. They turn litmus paper blue, so blue instead of red, if it's basic. The pH is going to be greater than 7 if it's basic, and it feels slippery. Now, you're not going to want to feel a strong base like sodium hydroxide with your fingers, because it's going to be dangerous, just like an acid would be dangerous. It's going to damage your tissues. But if you've ever felt, everyone's felt soap, right? Soap is actually basic. And if you go back to how soap tastes, if you've ever had your mouth washed out as a kid for using bad language, it tastes bitter, right? The reason that that's an effective punishment for some kids is because it tastes terrible. It tastes bitter. And especially small kids can't stand that taste, just like medicine tastes bitter if it's not sweetened up by anything. So if you think about soap, of course it tastes bitter and it's slippery. That's because it's basic. Okay. So let's go ahead and talk about how we define acids and bases chemically. All right. So the first person to come along and define an acid chemically on the molecular level was Arrhenius. Svante Arrhenius was his name. And he said that an acid is anything that increases the concentration of hydronium, and hydronium is just a polyatomic ion, when that acid is dissolved in water. So you can kind of look at this as two steps. If you have an acid, and I used HCl earlier, and you dissolved it in water, so we always put the water over the arrow when we dissolve something, it's just going to break it up into its two ions, H+, or you could just call it a hydrogen ion, and a chloride ion. Okay? But then what's going to happen after that is that H+ is not very stable, because if you think about what H+ would be, hydrogen is only made up of one proton and one electron. So if you're just taking away the nucleus and leaving the electron behind, which is why it has a positive charge, essentially an H+ is just a proton. It's a proton without an electron. Most hydrogen atoms don't even have a neutron, so an H+ is just a proton. Well, what tends to happen next is that proton tends to grab on, so if this is my H+, it tends to grab on to water, because this is happening in water, right? So, and here's my water molecule. Now, water is fairly stable, but these lone pairs can become a place for bonding, especially to something that doesn't have any electrons at all. So what happens is this H+ comes over and uses both of these two electrons to covalently bond to the water molecule, and the result of that is going to be this. It's going to be, and I'll put it in brackets because it's a polyatomic ion, it's going to have a +1 charge. So this is the hydronium ion that Arrhenius is referring to. All right. So if I write the equation, instead of the Lewis structures, but the chemical equation for what just happened, H+ reacted with H2O to give us H3O+. So if I look at what's in green, this is step 1. This was just, the blue was just an explanation of what's happening in step 2. So I have a two-part reaction. Okay, so 2 steps, right? So if I add those up and think about what cancels, well, what cancels on both sides? Okay, so our hydrogen is produced and then consumed, so it's going to cancel. And so what I end up with is an overall equation that says HCl plus H2O yields H3O plus plus Cl minus. So what we've just written is called an acid ionization equation. Okay, that's what that is an example of, and we'll do some more examples in class. Now bases are a little different. Bases increase the concentration of hydroxide when dissolved in water, and they're a little bit simpler. They're just going to be one step. They don't actually have the step where we're reacting something with water. It's just going to dissolve in water. So we're just going to do the part where we have the water above the arrow. It's going to split up into K plus and OH minus. And that's it. That's our base ionization. All right. So, for example, if I did another one, if I have calcium hydroxide, again, it's just dissolving. So it's going to be calcium with a 2+ charge, and it's going to give me 2 hydroxides, right? So I have OH2 on the other side, so I have to balance that by having 2 hydroxides on the right. Those are both examples of base ionization. All right, the last thing we have to talk about is how do we name acids? That becomes an important part of this unit because we're not always going to give the formula. Sometimes we'll give the name, just like with ionic and covalent compounds. So we have to have that system in place. All right, so what is the system? An acid is always made up of hydrogen and then a negative ion. Okay, so HCl is the example we've been using a bunch. The acid is named according to the anion. And the anion here, the negative ion, is chloride, right? That's what that's called. All right. So the rule is if the anion has an ending of IDE in its name, the acid is going to be hydro, put that in quotes, and then the base, and then ic, and I guess I should leave that the quotes open for a second there, and then the word acid. Always ends in acid. Okay, so what I'm saying here is, for this one, instead of chloride, I'm going to take that base chlor and put it right here as the base between hydro and ic. So therefore, HCl, this is my example, HCl equals hydrochloric acid. So again, hydroic acid, because the negative ion, the anion here, ended in "ide." Okay? All right. So what if we have a different acid? This time, let's say we have hydrogen paired with sulfate. And notice I have 2 hydrogens because sulfate is -2. So here the anion is sulfate. So the rule is if the anion ends in ATE, the acid is going to be just the base plus ic acid. So the only change is no hydro prefix. So it's not hydrosulfuric acid. H2SO4 is simply sulfuric acid. So again, just the ic instead of the ate, and of course we always end with the word acid. All right. And then there's one more rule that I'll give you. If we have, let's say H2SO3, all right, so that is hydrogen and sulfite. So that's my last rule. If the anion ends in ite, the acid is going to be, again, no prefix, but instead of ic, it's going to end in us, O-U-S, acid. So this one is going to be not sulfuric, but sulfur-us acid. Okay? So the ite becomes us, ate becomes ic, and ide is hydroic and ic. Right? That's the only three rules that you have to know. Bases, we don't even have to take notes on naming bases, because bases, if we go back up to our example, or two examples I should say, it's not a new system. KOH, we've always called, or at least for the last, since September when we learned about naming ionic compounds, and we learned about polyatomic ions, we've always called this potassium hydroxide, and that's what we're going to call it here. Just because it's a base, it doesn't get a different system. And then calcium hydroxide, same thing. It's just going to be something hydroxide. Now we'll learn later on when we get into weak bases that not all bases actually end in hydroxide, but we don't have a separate naming system for those weak bases. So for the time being, you can kind of just assume that every base is going to be the metal plus hydroxide, and that's it.